6 is looking at technology and the impact technology has had on science. And our first part here is looking at how technology can help with scientific investigations. And so there's a few examples within the module, and there's also some things to consider about the limitations of technology when it comes to these investigations. Now, you probably would have started maybe by looking at some experiments. And this first one here, quite a simple experiment, which is looking at the effect of temperature on a reaction rate. And it's a pretty easy setup. Normally you just use a thermometer, you might be using a stopwatch. If you want to get a bit more advanced, you might also be using data loggers. And so in this case here, you're seeing how does temperature affect a reaction rate? And it's a pretty straightforward thing that you do in labs most of the time. Now in this case here, what we're doing is we're looking at temperature. And so in this case here, this is what happens in the reaction. Simple chemical reaction, A plus B is equal to C. And in general, you've got there the idea that as you increase time, the amount of product produced also increases. And you should, for the most part, get this nice little linear curve. Now, what you would do is change the conditions. So in this case here, if you make it cold, or in the first example here that we'll see, if you make the conditions hotter, the rate of reaction increases. If you decrease the temperature, then the rate of reaction decreases. And it's a pretty standard idea, and it's pretty easy to grasp that. Now, most of you would hopefully have been able to do this in the lab, but even if you haven't, something like this is a very basic simulation. There's plenty of simulations out there that you can have a look at. And just remember that when it comes to working in the HSC exam, the people who mark your exams, they don't particularly know whether you've done this experiment or not. They just need you to understand how the experiment works. Now, what is the second experiment is the effect of temperature on the volume of gas. And this is a fairly easy thing, I think, conceptually to get. And you think, well, if you increase the temperature, then most likely you're going to get an increase in volume. Now, if you want to do this at a really, really simple level, probably the easiest setup is using a conical flask and a balloon. You have a bit of water in the bottom of the conical flask and you heat that up. And you can quite easily see that the balloon starts inflating. If you take that balloon and cool it down, then you'll see it deflating. And so this is a little simulation. Apologies there. This is a little simulation that can see that there and see that as you increase the temperature, the volume increases. Now this one here, speed on distance traveled. Again, you might have done this just on an oval or a long space there where you can quite easily get people to run a reasonable different distance. You might have used a stopwatch, might have used a trundle wheel or a long measuring tape. If you wanted to be fancy, you might have used a GPS app on your phone to measure your distance. Now this here, the simulation you can see here is comparing two cars. The one on the left is traveling at a high speed, the one on the right is traveling at a lower speed. And what we're going to look at is after 10 seconds, the distance they've traveled. And so in this case here, the one on the left is traveling about 280 meters. The one on the right is traveling about 80 meters or so. And so all you really need to look at there is the idea that the faster you're going, the more distance you're going to travel. The last little one here is this little thing here, pressure on volume of gas. And what you can see here is the idea is that if you increase temperature, then the volume is going to decrease. You might have done this here, as you can see there, this is a thing called Boyle's law, and a lot of school laboratories and school science departments have a little thing called the Boyle's law apparatus, which is essentially just a syringe on a fancy stand. And you'll know that if you've played with that, you can actually decrease and decrease, but you can never actually get it to zero. And so what you've got there is the pressure is the more pressure you exert, the smaller the volume, You may also notice that sometimes if you keep on doing that, such as with a bike pump or something like that, you also get some heat given off as well. Now, in any of those investigations, now whether you're talking about those 4 investigations or you're just talking about investigations in general, you will probably at some stage have to be asked or have to consider errors. And errors in science, like a lot of things in science, the word error doesn't mean a mistake. It just means something where you can't quite exactly get the exact value of something. And in general, we talk about 2 types, random and systematic errors. And so random errors are just fluctuations in your data. For the most part, it's very hard to get rid of random errors. If you're doing an experiment in your lab, it might be because maybe one part of the room is slightly colder than the other, or maybe there's a bit of wind or something like that there. Maybe there's a bit of parallax error where you're not reading the thing such as a graduated cylinder from a perpendicular position. Also, you might have the instrument there. If you're doing an electricity experiment and using some old style voltmeters and ammeters, maybe you've only got a small range of numbers there, or you're guessing slightly a little bit there. And random errors are the reason why we repeat experiments. One, it helps with our reliability. We know that we're getting similar things there. But what you do with the random errors is that if you take many measurements, you average it out and you get a very close to the actual value. You can also maybe go to a digital instrument instead of an analog one, but there's many ways there. Systematic errors are things though that you can get rid of. They're things that your experimental design should be trying to reduce as much as possible. And so you've got 2 sorts of ones here. One is the zero reading. So the most common probable example that you've been used to there is if you're using something like an electronic balance. Now, the modern electronic balances are very susceptible to fluctuations. And if it's been turned on for about half an hour, it may start actually going away from the zero reading. So even when there's nothing on it, it might read 0.1 or might read minus 0.1 or something like that. And that's why all those balances usually have a zero function on them. Another one, maybe in junior school, you've used the spring balances, and they usually have a little nut at the top that you have to adjust. Make sure that before you put anything on there, you get a zero reading. You also have degrees of accuracy. And so you've got here something that you've got to take into consideration, particularly when you're making measurements that are potentially very small. And this is something particularly in physics and chemistry that needs to be taken into account a lot. Now also when you're rounding, you've got to be very careful. Are you rounding up too early? If you need your numbers for calculations, maybe you need your more precise number till later on. You may also have significant figures there, and your measurements may be to 2 decimal points. That means your final answer probably doesn't need to be 10 decimal points. And you've also got there when you're measuring. Your measurements may be if you're measuring distance, might be centimeters, it might be millimeters, and you've got to make a judgment on the closest value to that there as well. Also, you can talk about errors, and this not so much in the IS course, but something to consider here, that you think about your measurement here. And so the example here, you've got a boat that's 20.5 meters, but your measurement is a 5 centimeter graduation. So your absolute error, so the error is about 5 centimeters, and you can go there. Now, and of course, precision is talking about how exact that is. And you also do have this idea, the word bias does sometimes come into errors, which is similar to what we're talking there about the systematic errors. Another thing to consider is that even though we can talk about technology in general terms, there are most technologies can fit into 2 types of things, one being analog and one being digital. Now, in the modern world, we are so used to everything being digital, particularly things like TV signals are all digital. If you're any internet data is digital data, but data can also be digital data is often just a representation of an analog signal. So we've got a lot of things to consider here, and so analog is just continuous. So similar to that wave pattern there, the analog signal is the wave. So if you are directly measuring, if you're recording a sound on a bit of tape, that sound is recorded in a wave. And then generally it's recorded as a sine wave. And so yeah, the examples there, when you're listening to something, even most car radios is probably still analog signals as well. Digital signals are discrete, and that means that they're very precise, and they're denoted by square waves. And so what that means is that it takes that analog signal and converts it into a series of numbers, which can be represented by those square waves. And computers, CDs, DVDs, not that people use them much these days, but any of your digital, any of your internet data, anything like that is done in that way. Of course, one of the last things to consider as well, and in fact, probably actually one of the first things to consider in an investigation, and often probably one of the most important things, is this idea of safety. And generally in science labs, we tend to focus on two areas. One is the chemical safety data, and just general work health and safety ideas. And so what we have here is a common way of assessing things is this IAC measurement: identify, assess, control. And so identify means that you've thought about the possible areas that risk can happen. And so there's an example here talking about fertilizers, and fertilizers contain chemicals that are quite dangerous to people, birth defects, cancer, things like that. Assess means you're making a judgment on the chances of these things going wrong and if there's going to be an impact. And so if someone is using fertilizers, you might say it's a medium risk, because there is a risk, but if you're controlling it, it's going to be fine. And the control, of course, is ways that you mitigate what's going on there. So if you're using fertilizer, you wear a face mask, you wear gloves, you wash your hands thoroughly, you don't inhale any of that stuff there. You can also go in a little bit more detail, and this matrix, safety matrix here, is something that is used particularly at industrial and university level. And it's the idea, it's taking that IAC protocol there and just going into a little bit more detail. And this idea that, low, medium, high, very high. And of course, if your investigation is going to go into that orange or red zone, you probably need to rethink your methodology. And of course, a lot of you are familiar with material safety data sheets. And this one here is just showing a couple of chemicals, so copper 2 carbonate and magnesium ribbon. And the thing is, most students will have at some stage handled magnesium ribbon, but there is a danger with it. And that danger comes about, burns and things like that. So often these material safety sheets and information are written at a worst case scenario. And so, but it's very important to consider that and think, well, just wait, no, that's not relevant to my experiment.